Okay, this is going to be the last topic for Chapter 7, LeChatelier's Principle. And to intro this topic, we're going to do a whole lab on this when we come back from spring break. But to intro this topic, let's ask this question here. If we have a reaction, our SO2, O2, SO3 reaction from the equilibrium video. If we have this reaction at equilibrium, which means the SO2 and the oxygen are combining and reacting, making SO3, and then our SO3 is at the same time decomposing into the SO2 and O2, all that's happening at the same rate. If I make a change at equilibrium, if I add more SO2, okay, so we've kind of like increased this right here, this concentration of SO2, we added more. What happens to K? Well, I want to remind you of something. K is a constant, right? Even we have this equilibrium expression. K is a constant. So the answer to that question is K doesn't change. Okay? So nothing happens to K. But something does happen, okay? Equilibrium is going to shift. Equilibrium is going to be affected. How does that shift or how does that change? Well, we want to restore equilibrium as quickly as possible. Okay? Equations are very stable when they're at equilibrium. So we want to restore the equilibrium. To do that, it's kind of like we've kind of made the scales a little imbalanced, okay? If we have this side is a scale, okay? And then this whole, actually just hold this whole reaction. We've got this little scale right here, and we've got this side and we've got this side on the scale. Well, we've increased the concentration of this, so we've kind of, we've in a sense, we've tipped the scale down because we added more of that side. We increased the concentration of SO2, so we've tipped the scale down. So to get the scale back to equal, what do we need to do? We need to kind of re-even out the sides. The way we're going to do that in a reaction sense, the way we're going to re-equal our scales, is we're going to run the forward reaction, and we're going to make more SO3. We're going to shift equilibrium back to the other side. And we do that by running the forward reaction, okay? So the answer is equilibrium will shift, and in this case, when you add more SO2, it's going to shift towards the products. And it does that by just running the forward reaction, making more SO3. Okay, now let's ask this next question at the bottom. What happens if I add more SO3? If I have my reaction equilibrium and I add more SO3, well, in that case, what I've done is I've tipped the scale down on this side. When I increase the concentration of this, tip the scale down this way, so I'll re-even out my scales. Okay, so in that case, I'm going to run the reverse reaction. I'm going to decompose SO3. This will just happen. You don't have to do anything. It will just restore on its own. So if we add more SO3, equilibrium will shift again to restore the original equilibrium, and it will shift towards the reactants. Right? So that's what happens when we make an adjustment to a system or an equation at or a reaction at equilibrium. So let's actually define what LeChatelier's principle says, because the scientist who studied this and learned this, he just put it into words, and he said, when stress is applied to a system, all right, a system being a chemical reaction at equilibrium, the equilibrium concentrations shift to relieve the stress. So when I was talking about tipping the balance or the scales back the other way, that's what I mean by relieve the stress. And you're trying to restore everything to its original conditions. So, kind of what we learned from the previous slide, if we increase the concentration of a reactant, we're going to shift right and make more product. That's what will happen. Equilibrium will shift right, make more product to restore the original conditions. And if we increase the concentration of the product, that was like the SO3 question up here. We said it's going to shift back to the reactants, and that's what it says down here. It's going to shift left to make more reactants. Now, the definition says when stress is applied to a system. So what does stress mean? What is stress? They can be a couple different things. It can be changes in concentration. And this can be concentration of reactants or products. We can change both things. It could be changes in pressure. Because we have, I'm going to scroll up. Everything up here is a gas. right? That's the physical conditions of these reactants. Everything is a gas, and gases can be compressed or they expand to fill their containers. So you can change the pressure by changing, for gases particularly. We can also change temperature. We could add heat to the reaction. We know that there is a delta H value associated with every reaction, or we can calculate one for every chemical reaction. So we could increase the temperature, and we could see how that's going to adjust equilibrium. We could also make things colder with temperature, so you can make things hotter or colder. And then lastly, we could do changes in volume. Change the volume of our, whatever the container it's in, we can change the volume of that container. Pressure and volume are kind of opposite things there, but we'll get to that in a minute. So we're going to walk through each of these: concentration, pressure, temperature, and volume, and see how changes affect equilibrium and how things will shift. Okay? So number one, changes in concentration. We kind of already looked at this, but let's look at it again. I'm going to read this statement on the left. If we add or take away reactant or product, the equilibrium shifts, but K stays the same. Okay? Remember, K never changes. So we have this reaction right here. Carbon monoxide gas plus hydrogen gas gives you methanol, CH3OH. CH3OH, and it's a gas as well. So I want to read these color-coded statements. This is a figure from your textbook. If it says if this increases, what is this? If we increase the concentration of CO2, it's like we tip the scales down on the reactant side. What's going to happen to tip the scales back is we're going to run the forward reaction. Okay? So we added more carbon monoxide. To tip the scales, some of that carbon monoxide is going to react with H2. And the concentration of H2 is going to go down because it's going to get used up in the forward reaction. And we're going to make more product, so this is going to increase. But remember, K stays the same. All right? Vice versa. If this increases, what is this? Methanol. If we add more product, we tip the scales down on this side. So we need to restore it. So we're going to run the reverse reaction to get it back to even. And so we're going to make more of both of these reactants. So H2 increases, concentration of CO increases. But K stays the same. And the way you'd represent this is you'd say concentration of CO is going to increase, or you draw upward arrow, and the concentration of H2 is going to increase as well. Over here, up on the first one, you could say the concentration of methanol, CH3OH, would increase. Overall, that would be the end result when equilibrium shifts left or shifts right to restore things. Okay, so that's changes in concentration. So if you, what if I want to ask another question though. What if I decrease the amount of CO2? What if I take some away? Well, what's it going to do? We want to replace the thing we took away, okay? So we need to make more of it to restore the initial changes, okay? So to do that, if we take away some CO2, we added stress to the system by removing it. We need to replace the CO2 that's been taken away. Well, how does this reaction respond to replace CO2? Sorry, I'm saying CO2, aren't I? How does this reaction respond to make more carbon monoxide, CO? It runs the reverse reaction, all right? So it's actually going to, this feels different from the scale thing that I was saying, okay? Here we take away CO2, so it's like the scales went up on this side because we removed some CO2. If you're still considering the whole scale problem, if I got a little scale right here, maybe I should use black. If I got a scale and I'm taking away some CO2, then this side would be lighter if you're imagining these as weights. I don't know if that's a good or a bad idea. So to get that side tipped back down even, we've got to make more of it. That's why we say equilibrium is going to shift back towards CO. So we can run all these scenarios, not just increasing concentrations on both sides, but what if we decrease the concentration of something? Equilibrium will shift to replace that thing. Okay. Again, if I just lost you, rewind it, listen to it again, read through this section of your textbook, or shoot me an email. Write down that question. Okay, how do temperature changes affect equilibrium? So we have this formation of ammonia reaction. Hydrogen plus nitrogen makes ammonia, and it's balanced. And the delta H associated with this is negative 20 kcal per mole. I gotta get a drink of water. Negative 20 kcal per mole. So remember, this is exothermic. And we view heat for reactions that are exothermic, heat as a product. So we could write that in as an actual product. So I want to read this statement right down here. If we increase the temperature, now we're going to start messing with stuff. We're going to apply some stress. If we crank the temperature up, heat it up, it is the same as increasing a product in this case. It's like we tip the scale, okay? We increase concentration of a product. So equilibrium is going to shift left, okay? Equilibrium is going to shift left. If we add more of this, we need to use up what we added, okay? So it's going to shift this way. If we add more of it, it's like we tip the scale down over here, okay? It's like we made that side heavier if we added more. I know heat doesn't actually have a mass, okay? So again, if that is whole confusing to you, just know if we add more of a product, we're going to shift the equilibrium left. We're going to use up some of that heat that we added to get equilibrium conditions back to normal. If we decrease the temperature, it is the same as removing a product. So what is that going to do? If we take some of this away, if we decrease it, okay, now it's like the scale. Equilibrium is going to shift right to replace the thing we take away. If you like the scale analogy, when you take some of that away, you made this side lighter if you take it away. So that's like we tip the scale up that way. So we got to run the forward reaction to replace some of that heat and get that side back down. All right, so depends on whether your reaction is exothermic or endothermic. Okay, so do not think these little statements with the stars by them are the end-all be-all. This is only for an exothermic condition, a reaction that's exothermic. If you have an endothermic reaction, remember, heat for endothermic is a product. So it'd be like heat plus A makes B and C. And endothermic, heat's a reactant. So then you have to play out the situations with heat as a reactant if you heat it up or cool down your reaction. It'd be different. Okay, that's temperature changes. Let's look at one where it is endothermic. Is heat considered a reactant or a product? Well, we just said if it's endothermic, positive delta H, we're going to write heat as a reactant. So now if we increase the temperature, which way does it shift? If we increase temperature, it's like we're increasing the concentration of reactant, so it's going to shift to the right. And if we decrease temperature, it's like we took away some heat. So here, equilibrium, I'm going to write it in, shifts right towards products. And if we decrease temperature, it's like we took away some heat. We need to replace the thing we took away. Okay? Play the scale scenario out. The side is now lighter, so it fell down. So we need to, it went up. It didn't fall down. Scales went up. So we need to make more heat. So we're going to shift the equilibrium left. Okay, towards the reactants to make more heat. If you take something away, equilibrium will shift towards that thing. All right, that's temperature changes. That's a scenario with exothermic. That's a scenario with endothermic. It's the only kind of scenarios you can have. Okay, pressure changes. The way we're going to determine an equilibrium shift with pressure changes is these steps right here. Number one, count the number of moles of gas on each side. So before we move on, let's do that. Everything in this reaction is a gas. So I've got a coefficient of 3 in front of hydrogen, so that's 3 moles of hydrogen gas. I've got a coefficient of 1 for nitrogen, so that's 1 mole of nitrogen gas. So total, that's 4 moles of gas. On the product side, I got a coefficient of 2, so I just have 2 moles of gas. Then let's play out a scenario where we increase pressure, and we'll play out a scenario where we decrease pressure. Scenario where we increase. If we increase the pressure, the 4 moles of gas will combine, so we're going to make our reactants react, and you're going to form product. We're going to shift to the side with fewer moles of gas to relieve the increase in pressure. We increased pressure. We added stress. So we're going to shift to the side. 2 moles of gas is going to put less pressure on our container than 4 moles of gas molecules. I'm going to say that again. 2 moles of gas molecules is going to put less pressure on our container than 4 moles of gas molecules. That's like having 2 people in an elevator versus 40 people in an elevator. Okay? To relieve pressure, you would want fewer people in there, fewer moles of gas in this case. All right? So equilibrium will shift to the right. In this case, because the right side had fewer moles of gas. Next statement, if we decrease pressure, 2 moles of gas break down into 4 moles of gas to increase pressure. So let me erase my little box. So here we are decreasing pressure. So the 2 moles, what's going to happen is the 2 moles of gas are going to break down into 4 moles. So we're going to literally run the reaction this way, decompose ammonia into hydrogen and nitrogen, so that we have 4 moles of gas. 4 moles of gas inside that container is going to apply more pressure to the walls than 2 moles. And if we decrease the pressure on our system, we want to run the reaction this way to create the side that has more moles of gas. Okay, so here in this scenario, because the reactant side had more moles of gas, equilibrium will shift left. Okay, now that's just for this particular reaction. Whoops. Sometimes the higher number of moles of gas may be on the product side, not the reactant side, and vice versa. Okay, let's look at this reaction down here with the sodium bicarbonate. 2 moles of HCO3, or NaHCO3, that's a solid. And then we've got on the product side a solid, a liquid, and gas. So we have 0 moles of gas on this side, and we have 1 mole of gas on the product side. So this one is opposite of that ammonia reaction up here. We have higher number of moles of gas on the product side. Now what happens? First question, what happens if we increase the pressure? We want to shift to the side with fewer moles of gas. So now equilibrium will shift left because the reactant side has fewer moles of gas. What happens if we decrease pressure? Equilibrium will shift to the side with more moles of gas. That's the product side, so it's going to shift right to the product side this time. Okay, please email me if this stuff is confusing to you. Reach out to me. I know it may be on spring break when you watch this or read this. We're going to do a whole lab on this, which will also help your understanding of this. I'm not going to give you, a big fat test on this right when you come back. We're going to spend time studying this more. So, but please shoot me your questions if this is all confusing to you. This stuff down here is just review, so we'll save this closer to the exam 3 time. That's it for LeChatelier's principle.